Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be discussing subbasin transform methods, specifically the user-specified S-graph method and the 2D diffusion wave method. All right, what I have on the screen here is HEC HMS. I have my watershed, and I've got it delineated into a number of subbasins. So I'm going to zoom in up on subbasin 1 here, and then we will use this subbasin as an example for the two different transform methods. I'm going to start off by just going ahead and clicking to select that subbasin in the model basin map. And as you notice over here in the Watershed Explorer, it got selected as well. So now in the Components Editor, the subbasin tab is selected by default, and we have all of our subbasin data right here, such as the area, latitude, longitude, and then the different methods. We're talking about transform methods in this lesson, specifically if you scroll down, the user-specified S-graph and the 2D diffusion wave. So if you're curious about any of the details for these other transform methods, check out some of the other lessons in this playlist. So we're going to go ahead and start by clicking the user-specified S-graph method. The S in S-graph method refers to the summation because this method uses a special summation unit hydrograph to represent the response of a subbasin to a unit of precipitation. So we're going to talk about some of the parameters here in the transform tab. So remember, these parameters we're seeing for transform tab are specific to the transform method that we selected, which is user-specified S-graph. All right, and what we have is an S-graph, a method, and a lag time. I'm going to come back to S-graph at the end. First, let me just talk about the method. We have a standard method, and when I select standard, all I do is specify the lag time. That lag time represents the length of time between the centroid of the precipitation mass and the peak flow of the resulting hydrograph at the outlet. So I could just type a number in here, 1.4 hours. If I wanted to select regression, I would also calculate the same lag time here in hours, but instead of me just typing in the lag time, it would use an equation. So if I select regression, now I have to specify some of the properties of the watershed or the subbasin, as well as a few exponent values. Okay, I'm going to bring the equation onto the screen here. This is the HMS user's manual. I am in the regression section of the user specified S-graph transform. So what we're seeing here is the equation. We have that time lag is what we're calculating. It's equal to this C coefficient times the length centroid divided by the slope with a couple exponents. So let me pull this over to the side and just show you that this length here is the length in miles, and it is the length of the longest flow path in the subbasin. So starting out the outlet all the way up to the longest flow path. The centroid length is going to be less than the total length, but it also starts at the outlet of the subbasin, and then it continues upward along the longest flow path to a point opposite the subbasin centroid. The slope here is in units of feet per mile, so careful with the units there. And that is again going to be the slope along the longest flow path. This next parameter is the roughness, and I believe that's this variable C here. So S is slope, and then C. The user's manual has a value of 0.79. I'll put that up on the screen in just a little bit, but it isn't. It's a roughness, so I'm not sure if it's definitely not Manning's N. That just seems too large of a number. The user's manual describes this parameter as the hydraulic efficiency of the stream, which is directly proportional to the hydraulic radius, but inversely proportional to the roughness. So I'm not sure if we type in the roughness here and it calculates that C value or what. But anyway, the exponents for M and P are values that you would just type in here. They're non-dimensional, and then they would appear as exponents for the slope and then this second term. If I scroll down on the screen here, you'll see some typical values. Now these values are in metric units, so something like slope of 2.08 would probably be closer to 10 or 12 if you convert it to feet per mile. So those are some typical values. There's that 0.79 for roughness. The user's manual also mentions that this equation right here is only good for US customary units. So people using metric would have to convert first. And last but not least, this S-graph here. This S-graph represents a paired data percentage curve. And what it is a cumulative runoff volume versus the percentage of the lag time. So let's just go ahead and create it first. So that might make it easier to explain. I go up to Components menu, Paired Data Manager. Next, I'm going to select the type percentage curves. So this is a percentage versus a percentage, and then click New. And then I'll give that paired data set a name, sgraph1. Typically, I like the name 1 for subbasin 1. And then I can close that. Up here in the Watershed Explorer, I now have a paired data directory, and inside that, a percentage curves directory. And here is my paired data set that I just created. My data source is either manual entry or DSS file. So if I select the DSS file, it would go ahead and require that I specify a file name and path name. If I go ahead and select the other manual entry, in that case, I would just go up to the table and start typing in values. I actually had some values typed in. You may have a blank table, but I was fiddling around with some values earlier. So the percent in the y variable, the dependent variable, would go from 0 to 100. And then the independent variable here is representing the x-axis or the percentage of that lag time. Back to the subbasin. And that is my explanation for what the user's manual says about the user's specified S-graph method of transforming precipitation to runoff. All right. The other method is the 2D diffusion wave method. So let's talk about that. I'll make that selection and then click on the Transform tab. This method is typically used for modeling extreme precipitation events, which involve nonlinear movement of water, which cannot be handled with the linear nature of all the unit hydrograph methods. This method can only be used with certain discretization and base flow methods. So, for instance, if you're using this 2D diffusion wave transform method, the only discretization methods you should use are either unstructured, right here, or file specified. And then also the base flow method needs to be either none, linear reservoir, or constant monthly. Make sure that you're using those. All right, so 2D diffusion wave, let's go back to that transform tab. After reading the user's manual about this 2D diffusion wave transform method, I've come to realize this is probably the most complicated or involved transform method, partially because it requires the modeler to create a 2D mesh within HEC-RAS. Yes, I said HEC-RAS. We're dealing with HEC HMS here, so there's requirement to use a separate program, and that's for version 5.0.7 or newer. Of course, I'm using HMS 4.12, so if you're using an HMS version later than 4.12, that HEC-RAS version requirement may be different. And then that 2D mesh within HEC-RAS needs to be imported into HEC HMS. The user's manual does provide a link to go learn more about that. But as far as this lesson, I don't want to go into too much detail, just letting you know that there's more to learn there. With that in mind, I do still want to talk about these parameters and what they mean. The first one is the implicit weighting factor. 1.0 is the default value, and the range is going to be between 0.5 and 1.0. It's used to weight the spatial derivatives between the current time step and the previously computed time step. The value of 1.0 would be the most stable solution, but least accurate. And then the value of 0.5 would be the most accurate, but the least stable. The water surface tolerance and the volume tolerance are the next two fields down. The value you're seeing here is 0.01, but the default value is 0.001 according to the user's manual. This basically represents the tolerance with regard to the simulation, moving on to the next time step or repeating the same time step. If the water surface error or the volume error is less than 0.01 feet, then that's acceptable and the next time step would be run. But if the error or the deviation exceeds the tolerance, what would happen then is the solver would iterate over the same time step again. The solver will only iterate as many times as the max iterations, which is set right here. And this value can be between 0 and 40. If the compute doesn't seem to be converging within the maximum iterations, you can increase the max iterations up to as much as 40, or what may be more effective is to increase the tolerance to improve the chance of the compute completing. All right, next up is the time step method, and there's two options here. There's adaptive time step and fixed time step. The only difference is if I select adaptive time step, then I also have to supply the max current number. This max current number determines the stability and accuracy of the simulation. It's used to ensure that the runoff doesn't travel more than one mesh grid per time step. And then here's the maximum time step here of 60 seconds. So if, for instance, it does travel more than one grid step, then the computational interval will be halved for the next time step. Below that, we have a warm-up period, so we can say yes or no. The default is no, but if we say yes, this is used to ramp up water surface from dry conditions to wet conditions. So if yes is selected, then we need to specify the duration of the warm-up period, say 1 hour, for instance, and then a fraction of the warm-up period would be basically between 0 and 1. It would be a fraction of the warm-up period where the model is ramping up to the actual initial conditions. 1/10 of an hour would be 6 minutes, but again, that's optional because you just always say no. The last value here is the number of cores, and the default is set in the tools. So if I go up to tools and then program settings, defaults tab, I see right here, the third item down is the number of cores. This is reading from my own machine, I believe. So you should have some numbers here as well. I better have one. And then, but as many as 12 for my particular machine. I'm just going to keep it at one. The number of cores used basically involves the amount of hardware that's being allocated to run the simulation. The more cores used, the compute will process faster, but there's also some limiting returns. All right, the last thing to mention with regard to the 2D diffusion wave model is that there's also a discussion about 2D connections. This is used to supply boundary conditions as well as link to other elements to and from the 2D mesh. I'm not going to go into the details there. The user manual speaks more about that. So with that being said, ends our discussion on the different transform methods. In this lesson, we talked about 2D diffusion waves and user-specific S-graph, but of course, there are others as well.